start with our first method, the recursion tree method. For example, we will use the recurrence t of n is equal to t of n over 2 plus t of n over 2 plus n. We are not writing down t of 1 or t of 2 because they are just independent of n, and then we are assuming that t of 1 is equal to a constant. Now to expand t of n, we can rewrite Tn as n plus 2 copies of t of n over 2. And then this t of n over 2 inside the formula can further be expressed as n over 2 plus 2 copies of t of n over 4 using the recurrence relation. And then if we expand this, then we will find that the formula is now becoming n plus 4 copies of t of n over 4. Now this is a nice pattern. We start from n and then 1 copy of and then 2 copies of t of n over 2. After that we get n plus n and then 4 copies of t of n over 4. If we do this further, we will get n plus n plus n and then 8 copies of t of n over 8. If we continue this process again and again, then we will get log n terms of n adding up together plus n copies of t of 1. Now t of 1 is a constant. So in that sense, if we add up all the things together, we will get something like big O of n log n. Now this expansion process, we can, instead of writing down using these words, we can also draw a corresponding recursion tree like this. So we begin with t of n, and then t of n can be decomposed into 2 copies of t of n over 2 and then plus n. So if we add these together, this is t of n. But each of these terms t of n over 2 here can each be decomposed into 2 copies of t of n over 4, plus something here, plus something here. And then if we collect all the things that we are going to add when we are doing this expansion of this term and this term, then after collection, then it is plus n here. So we will see that if we continue this process, we will get another level, and then we will have plus n, and so on and so forth. And after log n levels, we will reach t of 1 here, and then we do not do any further expansion. So in that case, t of n is actually equal to the terms that we are going to add here, plus all the leaves, t of 1 here. And using this is actually the same way as we are expanding using the horizontal method like this, line by line. But the good thing about this tree presentation is that we can easily tell the readers that, oh, there are some patterns about the terms that we are going to add in each level. And then we get a nicer presentation, so it is easier to see what is going to be added in a tree than what is written down line by line. And sometimes it will save us the time on writing down all the things, because with a tree, then we may omit some of the plus terms and it is clearer. Okay, so let us now see a different recurrence for our second example. This time, t of n is equal to t of n over 3 plus t of 2n over 3 plus n. Okay, so how does the recursion tree look like? So we have t of n here. So when we do the recurrence, then we will see that t of n is decomposed into t of n over 3, t of 2n over 3, and then plus n. Now this t of n over 3 will then be decomposed into t of n over 9 and then t of 2n over 9 plus n over 3. Okay, And then t of 2n over 3, for this one, it is now decomposed into t of 2n over 9 and t of 4n over 9 and the term 2n over 3. So if we collect all the plus terms that we are going to add extra here in this level, it is going to be plus n. So the process of expansion will go on step by step, and then we can see that after a certain number of levels, actually there are log n base 3 levels, because each time we are dividing the term of n by a factor of 3, so that we can't go that far. So there are log n base 3 levels here on the leftmost path. Then we cannot go further on the leftmost leaf. And up to this point, we will see that every level we will be adding n. So we have a lot of plus n here. But if we focus on the rightmost path, then we will see that it is not decreasing as fast as the leftmost path. Instead, although we are dropping by a factor of 3 in the denominator here, but then we will add back a factor of 2 in the numerator. So we are essentially dropping by a factor of 1.5. So the height or the length of the path on the right hand side is actually log n base 1.5. And after the first log n base 3 levels, we don't have altogether everything to go on further. So we will see that each level after that will have an extra term less than n to be added. So somehow this describes what are the things that we should add in the end. Then using this expansion process or this presentation, we will see that for the first top log n base 3 levels, each level is complete and will have n as an extra term to be added. So in that case, t of n, just considering those terms, we will see that t of n is at least n times log of n. So it is omega n log n. But on the other hand, if we focus on the rightmost path, then we will see that there are at most log n base 1.5 levels. And then each level has the term less than or equal to n to be added. So in that sense, t of n is equal to big O of n times log of n. Now we have an omega term, we have a big O term, and these two functions are the same, so we can conclude that t of n has a tight bound of theta of n log n. So isn't that simple and nice, right? So this is the recursion tree method. And now let us move on to the substitution method. So we find that sometimes when we are given a recurrence relation, we may be able to guess the solution of this recurrence based on our past experience. So for instance, let's say we have t of n is equal to t of n over 2 plus 1. Now here, let's be a little bit more specific. So n over 2 may not be an integer, so we take the floor of n over 2 to round it down to the closest integer, smaller than or equal to this number. Now if we look at it, then this time bound is the same as what we are doing the binary search, right? So we have one step to compare the middle term, and then the resulting part will only have half of the array to be sorted, to be searched. So in that case, the time is t of n over 2. Now if we remember this, then we may guess t of n is of the order of log of n. So we may guess t of n is less than or equal to some constant c multiplied by log of n. And then if we guess something like this, and if it turns out to be true, then we get t of n is equal to big O of log n. Now we have this guess. So this is the guess that we have. Then we can try to verify the guess by using induction. So what is meant by induction? Okay, recall a little bit about what you have learned in the discrete math course. We are going to assume that the guess is true for small values of n, and then we show that the guess is also true for larger values of n. And because of this, then if this is done, then we can see that the guess will be true for all the values of n. Now, in the induction process or in the induction proof, we made an assumption that small things work, and then use this assumption to plug it in, to substitute this assumption into the remaining part of the proof. So this is the so-called induction step, and then continue to solve for the case when we have a larger n. So that's why if we are going to use this induction method to prove that the guess is correct, people sometimes refer it to substitution method. But in my opinion, it seems to be better calling this method as the induction method. Yeah, this is just the induction. Okay, let us see an example. This time, let us go back to the recurrence that we have just seen. T of n is equal to T of n over 2, but taking the floor here, plus 1. And for this, let us use n is equal to 2 as the basis case. And we see that T of 2 is equal to T of 2 over 2 floor, so which is T of 1 plus 1, right? And T of 2 is equal to T of 1 plus 1, and then T of 1 is equal to 1. This is a constant, okay? So it is equal to 2. And we want to show that it is smaller than or equal to C log n. Now, so we can use C as 2 here, so it is less than or equal to 2 log 2. So this is the basic step for the guess, and now we assume that T of n actually follows the guess less than or equal to 2 times log of n in general. And we assume that this is correct for n is equal to 2, 3, 4, up to a value of k. We want to show that based on this assumption, it will also work for larger value of n. So for n is equal to k plus 1, then we will see that T of n is equal to T of n over 2 plus 1. So this is just a copy. But knowing that after taking the floor of n over 2, we will have a value strictly less than the original value. So in that case, T of n over 2 follows the assumption, and then the assumption says this will be less than or equal to 2 times log of this number. So by the assumption, we plug in the assumption, substitute the assumption here, we will find that T of n over 2 is less than or equal to 2 log n over 2, and then the plus 1, we copy it. Now this log of n over 2 floor, in turn, is less than or equal to log of n over 2 without taking the floor. So we now get this one. And 2 times log of n over 2 is equal to 2 times log of n minus 2 times log of 2. So this first term here, 2 log n over 2, will now become 2 log n minus 2. And after you add 1, this will be less than or equal to 2 times log n. So T of n smaller than or equal to 2 times log n for n up to k implies that T of n less than or equal to 2 log of n will be also true up to k plus 1. So this is the induction process, and now we see that this formula will be true, or this guess will be true for all n greater than or equal to 2. Okay, let's try to use this method to solve another recurrence. Suppose this time t of n is equal to t of n over 2, taking the floor here, plus t of n over 2 taking the ceiling here, plus 1. So the floor gives the rounding down process. Okay, actually it's not rounding but unconditional rounding. So we take the largest integer smaller than or equal to n over 2 here. And for this side, it is rounding up unconditional round down. So we are getting the integer smallest integer. This is the largest integer smaller than or equal to n over 2. And we get the largest integer, smallest integer here, smaller than or equal to n over 2 for this one. Okay, and then actually this recurrence corresponds to the time to find the maximum of n items using recursion. So what does that mean? Okay, we have an unsorted array of n numbers. We want to find the maximum of them. So we may cut the array into two halves. First, finding the maximum of the first half, and then finding the maximum of the second half using the same recurrence. And after that, we compare the result of the maximum of the first half with the maximum of the second half using one extra step, so that we get the maximum of the whole array. So this is the recursion way to find the maximum of n numbers. And then if we want to guess, then probably we will guess t of n is of order of n. So let's see if we can show that t of n is less than or equal to Cn for some constant c, and using this induction. Okay, so we try. So this is the recurrence formula. And now let us also use n is equal to 2 as the basis case. We will see that t of 2, so we plug in n is equal to 2 here. So this will give us t of 1, this will give us t of 1, and then plus 1. Okay. And we want to show that this is less than or equal to c times 2. So we can simply use c as the red 2 here for the c. So we find that this is less than or equal to 2 times 2. So we move on. And suppose that t of n is less than or equal to 2n for n up to k. Now when we move on to look at the larger value of n, so this time n is equal to k plus 1, that t of n is equal to this one, and then t of n over 2 will be less than or equal to 2 times n, so we get this one. T of the ceiling of n over 2 will be less than or equal to 2 times the ceiling of n over 2. Now notice that here this is a little bit tricky. Okay, there is no guarantee that n over 2 ceiling will be a smaller value, a strictly smaller value than n. So for instance, when n is equal to 1, then n is equal to 1, then this is t1. And then 1 over 2 is 0.5. Taking the ceiling, we get t1 again. So we get the problem. But luckily, we are now considering only the cases when n is greater than or equal to 2. In such a case, then no matter which n that we talk about, the ceiling of n over 2 will be strictly smaller than n. So we can apply this assumption so that t of n over 2 ceiling will be less than or equal to 2 times n over 2 ceiling. And then we copy the plus 1 here. So this is what we get. 2 times n over 2 floor plus 2 times n over 2 ceiling. After adding these two, it will always be equal to, exactly equal to 2 times n. And then we have a plus 1. So using this assumption, we get t of n is less than or equal to 2n plus 1. But unfortunately, this is not what we want. Recall that we need t of n to be less than or equal to 2n. When we cannot get that, then the induction is failing. So it doesn't work. So we don't get the desired bound 2n here. So the previous attempt failed, but actually we are not that far from the correct proof. The main problem of the previous attempt is that we are a little bit too humble. What does that mean? We are only making a weaker guess than what we need, so that during the induction proof process, we cannot take enough advantage of the assumption. So we make a weaker guess so that the assumption is weaker. So in that case, it is more difficult to prove what we want. So this time, let's start with a stronger guess. So previously, we tried to show that Tn is less than or equal to 2n. But here, we make it even stronger. Not just smaller than or equal to 2n, but smaller than or equal to also 2n minus 1. So let us use this guess instead. Now, if this guess is correct, then T of n is still big O of n, right? So let's see the effect of using the new guess. So again, we solve this again. So we have this one. When n is equal to 2, T of 2 is equal to T1 plus T1 plus 1 and 3, and it is indeed less than 2n minus 1. Okay? And now we have the new assumption. We assume that T of n is smaller than or equal to 2n minus 1 for all the values of n up to k. And based on this assumption, let us examine a larger n. N is equal to k plus 1. So this time we copy this, and then this is smaller than or equal to 2 copies of this one minus 1 plus 2 copies of this one minus 1 plus 1. Now if we collect terms together, this 2n over 2, 2n over 2 adds up to exactly 2n. Minus 1 plus 1 adds up to minus 1. And this is working now because we now get Tn less than or equal to 2n minus 1. This is what we want. So now, by correcting the guess, making it stronger, and suddenly it works. So this is the substitution method. And finally, let us look at the master theorem. Okay. Now, with the previous two methods, we will often need to show the upper bound and the lower bound, so in the asymptotic sense, separately. But when the recurrence is in a certain specific form, so Tn is equal to a copies of Tn over b plus some function of n, if it is in this form and satisfying some condition, then we may apply the so-called master theorem and get the asymptotic bound immediately. And this asymptotic bound is a tight upper and lower bound. So the upper bound, big O, and the lower bound, big omega, they match each other. So the master theorem is known for a long time. In the 1980s, and people use it. So we will just claim that it is the master theorem without the need of proving other things. Okay. So there are altogether 3 cases for the basic form of the master theorem. So we are all dealing with Tn is equal to a times Tn over b plus Fn. And for the first case, the f here is a small value. It's small. So we will see what is meant by small. Okay. So we compare the function Fn with this function n to the power log a base b and then minus epsilon. If it turns out that Fn is upper bounded big O, okay, of this one, then T of n is equal to theta. So we will see that this is the tight bound theta of n to the power log a base b. So the intuition here, so we will see in the following figure. Okay, so first of all, let us understand what is the term n to the power log a base b. So if we look at the recursion tree, n to the power log a base b is equal to the number of leaves. To see this, okay, n to the power log a base b is the same as a to the power log n base b. The reason is that if we take log, okay, then then we will see that this term is equal to this term. And then if n is small, then the final result of Tn will be dominated by the leaves that we need to add. So roughly speaking, this is the recursion tree for the recurrence formula. T of n will be equal to a copies of Tn over b adding up together plus function of Fn. And each of these Tn over b will then be another a copies of Tn over b squared. This is another a copies of Tn over b squared. And then if we add terms together, there are going to be a terms of Fn over b, and so on and so forth to be added here. The number of levels of this tree, we see that focusing on the leftmost path, each time we are dropping by a factor of b. So the number of levels of this tree is log n base b. But then for each level, we will be expanding the number of nodes here from a to a squared to a cubed and so on and so forth. So the number of leaves, which is T1 here, will be equal to a to the power the number of levels. So a to the power log n base b. So for case 1, we are saying that there's so many leaves here, and then this f of n, so that even if we add up all the things here, it is still not comparable to what we are going to add for the leaves. So in that case, for this case 1, T of n is equal to theta of the number of leaves. Okay, so this is master theorem, the basic form, and this is the first case. Okay, now this case handles the case where f is small. So the next one we are dealing with, f is going to be a moderate value. So this time we are comparing f of n with n to the power log a base b, and we find that f of n is equal to this one. Okay, it turns out that it is equal to this one. So if this is the case, this is not big O. Okay, so I made a typo here. This is actually theta. Okay. Then in that case, T of n will be equal to theta of n log a base b multiplied by log n. So we have an extra log n factor in the Tn term. So the intuition is that the added term of each level in the recursion tree will be the same, and it is the same as the number of leaves in the bottom level. So this is what we are going to expect. So the same figure as before, number of leaves is a to the power log n base b, but then we have fn for each level, and then each of these fn is the same as the number of leaves. So if we add up everything, they are going to be all the log n copies of the number of leaves. So that's why we have log n multiplied by the number of leaves here. So this is the second case. Now for the third one, so this time f is large enough, but not too large enough, we will see. Okay, so first of all, this time f of n, when you compare this with n to the power log a base b, so we find that f of n is greater than or equal to n to the power log a base b plus a little bit epsilon here. So fn is much larger than the number of leaves in the recursion tree. But on the other hand, we require that fn is not that large. Okay, so somehow, okay, we require that a times f of n over b is less than or equal to c times f of n. So we will see the meaning here. Okay, now in that sense, then T of n is dominated by what we are going to add at the first level. So T of n is theta of f of n. So how does this refer to? So here, this is the same recursion tree, and then the first level is f of n, and we see that f of n is much larger than the number of leaves, so we can just forget this. And now for the next level, it is less than or equal to c times f of n. And actually, the next level, it is less than or equal to c squared times f of n. and so on and so forth. So if we add things here only, then we will get fn, and then cfn, and then c squared fn, and then c cubed fn, and so on and so forth. Now we have this condition, c is less than 1. So in that case, this is the sum of, so this is the sum of geometric terms, so we call this a geometric series, okay? So it adds up to a certain constant times f of n. So that's why we will get theta of f of n, because it is at least f of n, right? Because just counting the first level, it is at least f of n. But on the other hand, it is at most a constant times f of n. So it is of big O of f of n. So together we get theta of f of n. So this is the third case that we want to introduce today. Now using the master theorem, then we have some examples here that demonstrate what happens for each case. So we are looking at Tn is equal to 9 copies of Tn over 3 in each of them, but then we are adding a different function here. So the first one is plus n. Now to apply master theorem, what we are comparing is we are always comparing this function n, n squared, and n cubed with the same thing of n to the power log a base b. N to the power log a base b is n to the power log 9 base 3, which is n squared. So in that case, if we have the recursion tree, the number of leaves is equal to n squared. And for our first example, this function value n here is much smaller than the number of leaves in the tree, so that t of n is dominated by the number of leaves, so it is of theta of n squared. Now for example 2, we will see that this function n squared is the same as the number of leaves, and we are actually adding the same n squared in each level of the recursion tree. So there are log n levels, all the log n levels, okay? And then each level we are adding n squared, so it is of theta of n squared log n in total. So this is the moderate f. And finally, if the function is n cubed, now this time n cubed is much larger than the number of leaves. So in that case, t of n is equal to theta of the first term, n cubed. Okay, and this is case 3. But note that, okay, master theorem does not cover all the cases where we are trying to solve Tn is equal to a times Tn over b plus Fn. So for instance, when T of n is equal to 9 copies of Tn over 3, but the function that we want to add, the plus part is n squared log n, it is more than moderate. It's not moderate. But on the other hand, it is not large enough. It's just a little bit more than n squared, but not large enough to be equal to n squared, n to the power 2 plus epsilon. So log n is negligible compared with n to the power epsilon. So it is not that large. So in that case, we cannot apply any of the cases that we have discussed. But on the other hand, if we cannot use master theorem that we know to solve it, actually we have a master theorem for this case, but not the basic form. But if we do not know, then we can always go back and use the recursion tree to try to solve this. And this is a challenge for you. So if Tn is defined in this way, then what is the asymptotic bound for this Tn? Okay, so you can try this as an exercise. Okay, now finally, before we conclude this lecture, let us solve this tricky recurrence. Now this time t of n is equal to 2 copies of t of square root of n plus log n. Now forget about what we are going to see in the following. You can cover it and see if you can solve this. Now the best way or the easiest way to solve this is we can use recursion tree. Using recursion tree, you can draw out how many levels that you have but you need to have a careful counting on the number of levels, and then what are the terms to be added in each level. And interestingly, you'll find that the terms to be added for each level turns out to be the same as this term, log of n. And then the difficult part for this problem is, what is the number of levels? Okay, so if you can count this correctly, then you get the answer. Now the second method, we are actually solving this in a tricky way by changing variables. So instead of solving this big Tn, we are going to define a new function. Let's call it s, such that s of log n is equal to Tn. So whenever you see Tn, it changes to s of something. And the relationship of the parameters here is, we have n here, then we will have log n. Now using this new definition of s, then Tn changes to s of log n. And how about t of square root of n? Now t of square root of n, if we change it to a function of s, we are going to log this one. By taking log of square root of n, we get log n over 2. So here, this 2 times t square root n is the same as 2 times s of log n over 2 plus log n. Now if you look at this, isn't it something familiar? S of something is equal to 2 times s of the same something divided by 2 plus that something. So s of m is equal to 2 times s of m over 2 plus m. So if you recall this, this is the same recurrence formula that we are using for the merge sort. So the solution is s of m is equal to m log m, or s of log n is equal to big O of log n log n. And s of log n is nothing but just t of n. So we find that t of n is big O of log n log n. Okay, so that's all for lecture 3. Thank you.